So, welcome everybody. Today we will have Heber that will share his learning journey on his understanding of some software design patterns. He told me that he will show how they relate to design principles and how they can fit inside the DS toolkit. So yeah, he's going to share his own slides. So Heber, whenever you want, the floor is yours.
You're muted.
You're muted, Heber, sorry.
Yeah, you're right. Sorry. Hello, everyone. Today, I'm going to talk about software design in general, but how this general concept might fit into the data science toolkit, right? So, just to give you a visibility of about the topics that we are going to cover, first we are going to start with the motivations. Then, once we understand what are the motivations for software design, then we are going to start talking about the principles, the patterns of software design. And throughout the whole presentation, I will be giving some machine learning examples and how they might be um, reshape in a way that they are complying with these ideas, right? Okay, let's start. But before to start, I just want to mention that I'm not an expert of in software design principles. I'm just a data scientist who wants to improve his code readability and maintainability over time, right? And this is not a comprehensive list of all software design patterns with examples and pros and cons. It's more like a summary of what I have learned during my journey to understand what they are and how should I use them. Okay, so I want to start with this question. Why do our designs go wrong? I mean, how can we possibly turn this nice looking DAG that we typically found in machine learning projects, loading data, preprocessing data, transforming some features, optimizing and feeding the model, and finally save the artifacts into what is known in the industry as a big ball of mud, right? A big ball of interdependencies that go all the place around, and you don't know how this method is being called whenever you are making some simple method or like higher level method call, right? Well, the answer is kind of simple because software systems, like everything else in the universe, tend to work out. I mean, whenever we start creating a machine learning model and eventually a machine learning system, we're going to take into account a lot of edge cases into our code. We're going to start with a class that is becoming bigger over time until it becomes really hard to manage and to anticipate where a simple change may collapse everything. We were going to have like business logic classes with a low level operations, such as things that are writing and reading files from the file system. Also, another like practice that we tend to use or tend to apply is object orientation programming abuse. And sometimes we introduce by accident or without knowing domain knowledge into the API and endpoints, right? So overall, it's going to move our software system into a more chaotic situation, right? And what do design patterns have to do with that? Well, they are common ways to solve those type of problems following two main principles. The first one, it's called program to an interface, not an implementation. And I'm going to, throughout the rest of the presentation, I'm going to start using interchangeably interface and abstraction because both words are referring more or less to the same concept. And the second principle is favor object composition over inheritance, right? I'm going to explain what they mean with code examples and so on and so forth. But before to going deeper into the principles, I want to mention two key ideas. The first one being abstraction, right, which means simplifying behavior and hiding implementation details. And the second is layering, which means divide our code into discrete categories, more or less like modularizing, but not just that, right? Okay, so let's discuss what I mean by abstraction. Let's say that we want to search for the word Glovo in DuckDuckGo with the standard library of Python, which is urllib. And our code in general will look like this, the low-level implementation. And we can start to abstracting some concepts and start using higher level modules, such as request here, for instance. And we can reframe the same piece of code in this way, right? But we can even go further and use directly the DuckDuckGo package and refactor the code to look like this, right? So abstraction means going from this type of implementation into this other type of implementation. I think, generally speaking, we as a data scientist are doing this abstraction really well in our code, right? The second is layering, which means divide our code into discrete categories. And I'm going to show you like a 3-layer architecture example, which is really simple. Let's say that we have the presentation layer, which we are going to use to share our model results to third parties, right? Then we're going to have the business logic layer that it's going to be in charge of training the model, making it work, standardizing inputs, and so on and so forth. Then we will have the data layer, right? Which is going to be in charge of gathering all the data from the database, pre-processing, just to make it work for the model, right? But it's not just about dividing our code into or trying to modularize our code into discrete categories. It's more like also how can we introduce rules on how the categories can talk to each other. If we are not taking care about that particular aspect, most likely we will end up having this big development, right? Okay. I will go back to the software design principles. Just to mention that the first one is program to an interface, not an implementation. But I would rather use the dependency inversion principle here because I think that it's works better for machine learning system. Okay, so I'm going to explain what it means. Okay, the dependency inversion principle means, well, it states two things. The first one is high-level modules should not depend on low-level modules. Both should depend on abstractions. And the second is abstractions should not depend on details. Instead, details should depend on abstractions. But I know that sounds like really abstract, and that's why I'm going to explain with an example each one of those statements. Let's start with the simple, right? Okay, high-level modules are things or are code that, generally speaking, our stakeholders care about, right? For instance, here we could have code that calculates, in our case, for our particular case, the estimated time to prepare of a given order, right? And on the other hand, low-level modules are things that our stakeholders, generally speaking, do not care about, right? Such as code that standardize data, fit a model, etc. So generally speaking, our stakeholders really don't care about if we are using a data frame to abstract the idea of a spreadsheet. They just care about whether or not we are going to predict the target variable. In this particular example, the estimated time to prepare well, right? So high-level modules should not depend on low-level modules. For instance, here we can see a piece of code that is predicting the ETP. ETP stands for estimated time to prepare. That is depending directly on low-level models, such as the idea of a data frame, or the linear regression here, or the transformer, which is a min-max scalar, right? Instead, both of them should depend on abstractions. For instance, the low-level estimator here, which is an abstraction by itself, depends on the abstract idea of an order, a data container or something like that, that help us to hold out the different attributes of an order. For instance, the ID, the activation time, the store, which by itself is another abstraction. And by abstraction here, I'm meaning something that helps us to model real-world objects into code, right? And the top level modules here, or high level modules, like the function that predicts the ATP, depend on the abstract idea of the estimator and the abstract idea of an order, like an interface. And that's why they mean by high level models should depend and low level models should depend on abstractions. Okay. Next, I'm going to talk about the second statement. So in order to illustrate this, because in code it's kind of a bit harder to see what is happening on behind, I'm going to use a car example here. On our car example, abstractions or interfaces might be something, things that we are used to work with, like for instance, the steering wheel, the pedals, or the lever gear, right? And on the other hand, details are, the things that are used to represent how the car actually works, right? For instance, we can think of details using the engine, right? The car engine. So, so abstractions, I mean, the interfaces should not depend on the details, right? And why? Because let's say that we then move from a regular engine to an electrical engine, and if the interfaces depend on the details, the engine, then it's more likely that they need to change in order to work with this implementation. And if that happens, then it's going to be really hard moving from, or at a customer level, it's going to be really hard moving from a regular engine to an electrical engine, right? So that's why details should depend on the abstraction. And the same goes for code, right? Okay, and the second principle, which is favor object composition over inheritance. In order to explain it, I'm going to show you an example. So, but in order to make it more clear, let's say that a common problem when using abstractions as a design strategy is inheritance abuse, right? That means specializing a class along different design axes at once. Let's see an example of what that means. Right. Suppose that we have, or that we move forward with this estimator interface or abstraction that we were talking about, right? And based on this idea, we decide to implement a linear regression model and an ITVM model, right, inside this estimator. So at the end of the row, we're ending up having these two implementations. By the way, this is an idea or like an example of the important and adapter pattern, right? That have this fit method that trains the model and another method that shares the artifacts over S3 bucket, right? So let's say, or let's imagine that one of our stakeholders came to us and asked us that, having a model that is or sharing the results over S3, it's working okay. But we should also implement another model that shares the results to a data warehouse, or let's say a system or file system, right? An LM IO estimator, LM data warehouse estimator, and LM S3 estimator, right? So we can like translate this into the different classes that we have, but here's the problem. Because we start by having one single design axis, which is aimed to model the different type of models, right? So in this axis, we will have the linear model, the ITBM, and a deep learning. Let's put an example here, right? And then we add another design axis, which is aimed to capture how can we share the results. For instance, here we will have the data warehouse, the S3, or the file system, right? So if we want to support every combination, that inevitably will lead us to an explosion of subclasses. I guess most of us are familiarized with this concept, right? So if we have a lot of classes, then we're managing them all across the different changes that we are including over time. It's going to be really painful. So here's one where the adapter pattern, which is some design pattern here, can help us to deal with this situation. So the adapter pattern states that the estimator class being responsible for both training the model and sharing the results is too complicated, right? So we can think about any mechanism for sharing results to be grabbed as an independent class. In that sense, we might end up having here an abstract idea of an outloader, a way to share the model results, and by itself, the estimator, which is composed of these two ideas, right? And this is how the adapter pattern can help us to overcome this challenge that we may face over time, right? And the second pattern that I'm going to show you here is the abstract factory with an example. And in order to show you this pattern, I want to go back to the three-layer architecture that we were talking about. The first part being the data layer, which is represented with this interface, the idea of a repository, right? This is also called the repository pattern, which has two implementations, an SQL repository, which simply gathers the data via a query from a database, and the IO repository that gathers the data from our file system. And then we can have the business logic layer here, which is represented by this abstract idea of the estimator with the two implementations being the linear model estimator and the light GBM estimator. And finally, the third layer part is that it's aimed to share our model results. It's represented with this abstraction here, the uploader, which has two implementation, S3 uploader and data warehouse uploader, just for simplicity, right? Okay, so we can compose these three different abstractions in a higher level abstraction, right? That represents our three-model layer architecture, which is here another abstraction, which is the class, right? That has an estimator attribute, a repository attribute, and the estimator by itself has this uploader attribute, right? And the task of creating a model might be seen as this simple series of steps, right? But as you can see, this class by itself allows like infinite or well, not infinite, but a lot of combinations or permutations of which estimator and which repository and which uploader we might use, right? So what happens if we want to introduce some constraints, for instance, that the light GBM estimator should only use the data warehouse to share the results. So in order to do that, we can introduce the abstract factory that help us to centralize the different configurations that are valid for our system, for our machine learning system. And we are going to delegate the responsibility of instantiating the object to it, right? In that sense, we may have like a model A configuration that it's composed of a linear model estimator, an IO repository, and an S3 uploader. And in parallel, we'll have the model B configuration, which is going to be the light GBM estimator, SQL repository, and data warehouse uploader. Okay, right? And then we are going to have this constructor here, which it's called build model, right? So that will be an example of how we can use two software design patterns in order to be complain with the software design principles. Okay, I know that at the very beginning I told you that we wouldn't go through like a comprehensive list of the different design patterns, but I think that up to this point it's worth to mention that there are a lot more, and there are mainly three classes of patterns. The first being the creational. We touch on how to use the abstract factory, but there's a lot more. For instance, the singleton, which is how the different databases connections are handled. You know, the engine from SQL Alchemy is hiding inside this session, so you can only have one single engine throughout through your whole application, as well for the login module, for instance, in Python. There's the structural category. We see how the adapter pattern may help us to overcome the subclass explosion problem. And also we have the behavioral, right? So there are a lot of them out there. And I think that one common question that I was asking myself recurrently is when should I use design patterns? And in order to understand or try to answer this question, I always try to refer to the stand of Python. You know, stand of Python is this Eastern egg that you can found by creating like a Python console and just typing import this. And it was wrote by Tim Peters, right? And I think that generally speaking, it suits really well, or it's really aligned with the global values. For instance, beautiful is better than ugly, explicit is better than implicit, simple is better than complex, and complex is better than complicated. I think that it really resonates with the care value. You know, we have to show care with the next generation of data scientists who are going to maintain the solutions that we are designing right now. And there's another, like here, for instance, special cases aren't special enough to break the rules, although practicality beats purity. I mean, this is also really aligned with the value of GAPS. You know, sometimes we have to prioritize impact over perfection. And I think, well, it were noticed that it's a really, piece of software for us, let's say, right? And finally, I would like to share some additional resources for those who want to learn more about this world. The first one, this is a data science project refactoring repo that you can go over, and there's also a series of videos that explain why some of the design choices were made. And also here's another great book, which is called Robust Python. I think it's really good, but the second one here, the architecture patterns with Python, it's really well, it's a really nice resource. It has become some kind of like a handbook for me whenever I have to take some decision on software design. Yeah, that's it. Thanks.